Hi, welcome back to Learn Level. In this video, as part of our series introducing proofs by worked examples, we're going to look at proof by contradiction. And the example we're going to use to learn about this is we're going to prove that the square root of 2 is irrational. And we could use our shorthand notation to write this. We could write root 2 is not an element of the rational numbers. So here this symbol is the set of rational numbers. And rational numbers are numbers which can be expressed as a fraction. So really we want to prove that the square root of 2 can't be expressed as a fraction. But before we get into that example, let's quickly go through how a proof by contradiction works. So, how it works. In a proof by contradiction, what we do is, so we want to prove a certain statement. We assume the statement is false. So we want to prove it's true, but we start by assuming that it's false, or we assume kind of the opposite of the statement. Then we do a whole bunch of correct logical steps, and eventually we reach something which doesn't make sense. We reach our contradiction. So the thinking behind a proof by contradiction is that if we assume that the statement is false and then perform a lot of correct logical steps and reach something which doesn't make any sense at all, it's a contradiction, it must be the case that our initial assumption is incorrect. Because it can't have been any of these steps which were incorrect. All of those were correct. So it must have been our initial assumption which was incorrect, and that's how we led to this confusing contradiction. And by laying it out in this way, we prove that that initial assumption is incorrect, so the statement is true. So keep this overall structure in mind as we look at our example. We want to prove that the square root of 2 is not a rational number. So it cannot be expressed as a fraction. And I'm going to write, we prove this by contradiction first, so that my reader knows how I'm going about this proof. They know to look out for the contradiction structure, which I went through before. So first, we assume, for the sake of contradiction, that the square root of 2 is a rational number. So I'm assuming the statement is false, but I'm assuming that with the purpose of finding a contradiction, to show that must be incorrect. Now, of course, we have to ask ourselves, what does it mean to be a rational number? So feel free to pause and have a think. Along the lines of what we learnt in direct proofs, we should ask ourselves, what does it mean precisely for a number to be rational? So hopefully you've had a go at that. Here is how we would write it. So, since the square root of 2 is a rational number, we can write it as a fraction. So that means it's something like p over q, where p and q are both integers. Q is non-zero, And there's one more condition we have to satisfy here, and that is that the greatest common denominator of P and Q is equal to 1. Now this is important, and it will play an important role in our proof. Think of it this way. We want to allow fractions like 2 over 3, but we don't allow fractions like 4 over 6. So we know that from the way fractions work, you can write a fraction in more than one way. 4 over 6 is the same thing as 2 over 3. But by enforcing that the greatest common denominator of P and Q is 1, we are taking the simplified fraction. So we're not allowing the fraction to be unsimplified. So that's a safe assumption. That's still a rational number. All right, so let's try and get a contradiction out of this. So the square root of 2 is equal to P over Q, and P over Q are integers. This means that if we square both sides, we get 2 equals P squared over Q squared. So we have that P squared is equal to 2Q squared. Now Q is an integer, which means Q squared is an integer. So this tells us that P squared is even. And from our video on proof by contrapositive, we know that this means P is even. So this step we have proven already in this video series by contrapositive. Okay, so this means that P is equal to 2m, where m is some integer. So that means that the square root of 2 is equal to 2m over q. So if we square both sides again, we get 2 is equal to 2m squared over q squared, which gives us that 2 is equal to 4m squared over q squared, which tells us that 2q squared is equal to 4m squared, which tells us that q squared is equal to 2m squared. And here we have a similar situation as we had here. Q squared is equal to 2 times some integer. So q squared is even, and again this tells us that q is even. Again from our proof by contrapositive. So q is equal to 2 times some other integer. Let's go with k. But hang on, at this point we have that q is some even number and p is also some even number. But we had to assume that the greatest common denominator between p and q is 1. So at this point, there's an issue. If p is equal to 2m and q is equal to 2k, 2 is a common denominator. Two is a common denominator of p and q. So the greatest common denominator of p and q cannot be equal to 1. Because it's at least 2, because we know that the number 2 is a common denominator. So the greatest common denominator is at least 2. So what we've ended up with is we know logically that the greatest common denominator of P and Q is not equal to 1. And on the way, we assumed that the greatest common denominator is equal to 1. So we're in a situation where the greatest common denominator is both equal to 1 and not equal to 1. That is our contradiction. So over the page, I'll write out how I would write the rest of the proof, because this writing in orange or red is more thinking than how I would present the final proof. So on the next page, I'll just finish off the proof from where we're up to. We've just established that Q is equal to 2k, where k is an integer. So the way I'd write the rest of the proof is, since P is equal to 2m and Q is equal to 2k, with m and k integers, we conclude that the greatest common denominator of P and Q is not equal to 1. But this is a contradiction. Since the greatest common denominator between P and Q is equal to 1, we assume that is true. So the assumption that the square root of 2 is a rational number must be false. So square root of 2 is not a rational number. And there we have proved that the square root of 2 is irrational. So hopefully you found that interesting. Proving that square root of 2 is irrational is a big proof. It's a classic example. It's okay if you don't understand the proof the first time you see it. That's fine. Feel free to watch the video again, go through it line by line, really unpack what it's saying, what it's meaning, and whether you believe the proof. Because at the end of the day, that's what a proof is. A proof is trying to demonstrate to you, lead you to believe that a statement is true. So good job getting through this proof. It's not an easy one. And with that, I'll leave you to it and see you in the next video where we'll look at a proof by induction.